Welcome to Spring LIB.
For this problem on the topic of electromagnetic induction, we are told that a long, thin solenoid has a given number of turns per meter as well as a given radius. Now the current in the solenoid is increasing at a uniform rate, and we know that the induced electric field at a point near the center and a certain distance from its axis is also given. And we want to calculate the rate at which the current is increasing di dt. So we know that the magnitude of the induced EMF, epsilon, is equal to the magnitude of d phi dt. So that's the magnitude of the rate of change of flux. And this can be written as the time rate of change d dt of the product of the magnetic field times the cross-sectional area of the solenoid A. So we'll write this as d by dt, the time derivative of mu naught times the number of turns per unit length in the solenoid N times the current I times the cross-sectional area A. So we just replace B with mu naught Ni. And since these are all positive constants, this becomes mu naught N times A, the positive constants, times the magnitude of the time rate of change of the current di dt. And we also know that the magnitude of the induced EMF epsilon is equal to the electric field strength E into 2 pi r for a solenoid. And so therefore we can see that the rate at which the current is increasing, di dt, is equal to the electric field strength E times 2 pi r divided by mu naught times N times A. And since we have these values, we can calculate this rate of change of current. So that's an electric field strength of 8 times 10 to the minus 6 in SI units, which is volts per meter, multiplied by 2 pi times the distance or the radius r of 0.035 meters divided by mu naught, which we know is 4 pi times 10 to the minus 7 in SI units, times the number of turns per unit length, which is 400 turns per meter, times the cross-sectional area, pi r squared, at pi times 0.011 meters squared. And so calculating, we get the rate of change of current di dt to be 9.21 amperes per second.